Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So we're delighted here to host Roger Myerson, who is a very distinguished Nobel Prize-winning economist. I know many people that are typically in the lab, and unfortunately many of them are traveling, have worked on stuff related to Myerson's famous work on optimal mechanism design. And we're very excited to hear what he has to say about sequential equilibrium distributions in multi-stage games. So thank you very much.
I'll get to work. I am lucky to be hosted here. It's been great to be in this amazing lab thinking about technology and the world and society and economics and everything else at this cutting-edge company. And this is old-fashioned. Well, this is not old-fashioned. It's cutting-edge also. But this paper is an attempt. This is not applications of game theory to anything. This is basic game theory methodology, trying to understand. And to me, since I've been saying for at least 24 years, I think the early 1990s, more than 20 years, I have certainly been saying that the great outstanding problem in game theory methodology is how to extend Kreps and Wilson's 1982 definition of sequential equilibrium, which is the basic concept of rational behavior, our basic way of characterizing rational behavior for finite games. How do we extend it to games where people are observing signals or have types out of infinite sets and are choosing infinite actions? For example, if firm 1 in the first stage of a game chooses a price for the first period, which is a non-negative number, and customers and other firms that they are competing with all hear that price, well, they had an infinite number of possible numbers, and even if we bound the price above by $7 trillion to make it compact, it's still, there's an infinite number of possible real numbers in that compact interval, and how do people react to that was what we have to say. And the hard part of sequential equilibrium is all about making sure that behavior is rational, not only in the positive probability event, but in the zero probability events that happen off the equilibrium path. So if I chose a price that surprised you, what would you infer about me, about my cost function or something has to be described. And there's a lot of inferences when things get infinite, and that's the problem. So yeah.
Can I just ask a question on an example? Because prices are discrete, right? So.
Well, I guess prices probably are discrete if you announce them in integer multiples of a penny. That isn't what people write down. So one answer is, what I thought when I saw Kreps and Wilson's paper is, any infinite game, I'll approximate it by a finite game, and it's the limits of those sequential equilibria are it. The problem is that there's not an obvious way of how to define what sequence or net of finite approximating games should we be talking about. And there are a lot of things that under certain obvious topologies you can approximate a game by, but that has just ridiculously different properties. So I'll try to get. The bottom line is this. I've got some definitions and some results. The existence theorem, the main existence theorem, has been proven for a class. Well, my co-author has written a ridiculously long proof that he and I are both dissatisfied with, and when it's too long, you say, "What, have we made a mistake?" And I'll show you the class of games for which the proof applies, and in some sense, it's a disappointingly narrow class. It's a broad class of games in some sense, but it's disappointingly narrow. I should not be able to prove existence for every equilibrium. For every game, for example, if we don't have compactness, or if we have with compactness, if we say whichever one of us chooses the lowest strictly positive number is the winner, there's no answer to that question. Anything we call an equilibrium would be unsatisfactory. Obviously, we choose numbers that are infinitesimally near zero, but which one of us is going to be lower?
Are you thinking of so price might be in pennies, but time, I suppose if you're bidding in time or something, then you might have there
I'm going to stick with discrete time. The truth is, time feels more continuous to me than for example, money. Right. By the way, we talk about money being discrete, but on the other hand, if I'm pricing in in dollars per gallon, well, I could talk about, if you think gallons are continuous, well, there are only atoms that are discrete, but you could say, how much volume of fluid will I give you for a dollar's worth? And then suddenly prices sound like they're very continuous. So it's, time feels, in my life, time feels very continuous to me, but there are serious problems we know with the game theory modeling of continuous time, and I'd be happy to talk about that if you'd like. You know what? Since I don't have that many, since my results are so unsatisfactory, and I really want to give you a sense of real problems with game theory, Robert Anderson has a paper which I hope has been published called Quick Response Equilibria, and in which he raised the following problem, but for decades it was unpublished. On his website it says that 2004 forthcoming somewhere, but anyway, and it's been a decade since then. Consider we're going to play the prisoner's dilemma game and repeat it in continuous time, and we're each agreeing we're both going to cooperate at time 0, and if at any point I have seen you, or let's say if I have seen you defecting for an open interval of time in the past, then I will defect. So that sounds like a meaningful strategy. You're following the same strategy. Start cooperating, and if there's any open interval in the past when I have been defecting, then you will defect. But what is the outcome? The answer is it's not obvious, because it's true that we could obviously be cooperating forever, and that would satisfy those strategies. But you can pick any number you like, say pi or 2, and say at all points in time after, consider history where at all points in time strictly after time 2, we are both defecting. Both of us at all times strictly after 2 can see the other one having some open interval been defecting, so that also implements a path. I have to say, I never heard Robert Anderson speak it, but Professor Ehud Kalai told me about this example years ago. That's how I know about it. So I'm going to stay with discrete time models and finitely many players. Finitely many players, discrete time, just people see infinite actions. I should say, so I'm not satisfied with our existence theorems, and perhaps because of the main theorem that's been proven, we have a proof, but it needs to be proofread by both of us much more, and so I'm going to say anything I call a theorem is really a conjecture, and the examples that I'm going to give you, most of them don't even fit the class of games where the proof applies, although it is a broad class of games. It occurs that you should know the term perfect Bayesian equilibrium appears a lot in the applied game theory literature, because these games where we want to talk about sequential rationality, Freudenberg and Troll, it's been mentioned that I have a Nobel Prize. This is not going to be my best work. It may be my best work because it's given the difficulty of the problem, but it's not going to be very impressive. And it's entirely possible that there's some obvious other way of looking at it that anyone in this room might suddenly see, and you may be right. Phil and I may have been thinking about this the wrong way. Phil Rainey and I, my co-author. Freudenberg and Tirole back in the 80s said perfect Bayesian equilibrium is a term that can be used for, well, it's like sequential equilibrium, but we only apply Bayes' rule when we know what we're doing. Well, when do you know what you're doing? It's just not been, it's never been precisely defined in infinite games. It has been, they wrote a paper in 1991 that is not Jean's best paper either. Jean, which they tried to define it, and nobody uses their definition, and they only define it for finite games, and no one's used their version. It was very complicated. Instead, I think the term perfect Bayesian equilibrium, and you're welcome to use it if you have already, and people who, as far as I'm concerned, perfect people who write an analysis of a game, like the one I just described. Firms observe each other's real number of prices, and they say there are beliefs that people have, and we want to make sure that they're rational even after being surprised. Perfect Bayesian and they say this is the perfect Bayesian equilibrium analysis. To me, I read that as meaning you're talking about a game for which the game theory methodology guys have not yet defined sequential equilibrium. You are too respectful to apply, to claim that something is a sequential equilibrium when nobody's bothered to formalize the definition. But you're pretty sure that when somebody bothers to formalize the definition in a reasonable way, whatever you're doing is probably a sequential equilibrium. And I think you're probably right. And that's what perfect Bayesian equilibrium means. And go ahead and use it. I don't have anything against people using that term. To me, the methodologists, like myself, should be enormously embarrassed that we don't have this. And we should be spending all our time working on it until we fill the gap. But as you can see, it's hard. Phil Rainey and I have been working for about a dozen years ourselves on it. Anyway.
Like for simple applied games where we have continuous time, right? Basically, I offer you a price, you accept or reject, you don't know my time. I mean, we do have the sequential equilibrium, what to do in those games.
Good. If you think so, good. It's not.
Like because we apply, like signaling games, right? We apply D1, even refinements.
You know what? If you can look at the game and you think you know exactly what discrete approximation you really have in mind, then all I can say is Kreps and Wilson's definition is for finite message spaces, and finitely many possible, we'll call it types. The state of your position or the state of all your information at some. I've often used type to mean a player's private information at the beginning of the game, but I'll use type. We use in this paper type to mean what players know at any point in the game. So a player's type in the middle of a game is everything that player has learned so far. And if you have infinitely many possible types in the middle of the game, because you could have infinitely many possible numbers, I should see what the problems are. Often it seems obvious the problems shouldn't arise. It seems pretty clear, but
For example, in that game, you could write define saying that, I have a conditional probability distribution over your types given the price.
Yeah.
And then I could define consistency saying that there are probability distributions converging without doing discretization or anything like that to this in weak topology, and therefore,
you get some difficulties. For example, one thing we could easily do, I could be either a high cost or a low cost type, and in equilibrium, both of my types are going to choose a price of 1. But let's say I can, let's just say I can only choose prices between 0 and 2. Nothing bigger than 2 is ever going to be considered. And you could imagine that when I'm the high cost type, I have some distribution that's concentrated around getting close to 1 as we look at a sequence. But if it's I don't know how do I want to do this? If I'm this is the high cost type, I say, and the low cost type has a lower distribution, then it looks something like that. I don't know. So that the density of the low cost type is near 1 is not as high. The likelihood of a low cost guy choosing a number exactly at 1 or in the very small neighborhood of around 1 is much lower than the high cost type. And also for far away tails, it's much less likely to be low than high. But there's an intermediate range just a little bit below or a little bit above 1, where the low cost type is more likely to make errors. And now we can say pick any number x, and say when you see that, what do you believe? And at 1 itself, in the limit of these distributions, you're going to believe I'm high, and at everything lower. And so if you take beliefs pointwise, you have trouble. So how do we do these conditional probabilities? How do you just? That's the kind of thing that can go wrong. And so now we get a problem that if you take pointwise limits of conditional probabilities conditional on an infinite number of signals, you can get the ex ante you thought it was 50-50 equally likely to be high or low, but ex post, if you take the pointwise limit of your beliefs, you always believe that what did I say? That you always believe that I'm high. So that's not right. Both at 1 and everywhere away from 1. But so you say, maybe we have to talk about beliefs on, I don't know. Anyway, and it doesn't integrate back. So Bayes' rule is derived from saying that your posteriors, when you multiply them by the probability of any given observation, posteriors after any given observation multiplied by the probability of the observation integrated back, the expected prior of the posteriors should be equal to your prior belief about the probability of any event. And the expected value of your conditional probability of your belief afterwards should equal your current belief. and we can easily generate point-wise limits. So we don't want that. Beliefs can't satisfy that. Can't violate that rule. Let me say it's important to say that there's a big conference on probability going on down at Harvard today that Microsoft is also advertising. Probability theorists don't think much about, this is very much a probability theory talk, but it's something that most probability theorists wouldn't be interested in, because the whole problem is beliefs after zero probability events. And I should remind you, if you don't know, that the reason why we have to worry about it is because if your beliefs after zero probability events would be too strange, you might then behave in a way which would cause me to try to make sure, unlike physics probability theory, in economics probability theory, people's perceptions of what would happen in an event can cause them to behave in such a way that they make that event happen with probability zero. So if we allow you to have crazy beliefs in a probability zero event, because after all we don't really know how to apply Bayes' rule after zero probability events, those crazy beliefs might cause you to behave in crazy ways that would make me want to prevent that event from happening, and now we've just built a self-justification for your crazy beliefs. We say, no, you shouldn't have crazy beliefs. And game theory should not assume that people would have crazy beliefs. Now the question is, what do we mean? So this is a slide that has too much on it, and it has all the notation. The notation is meant to be fairly standard, and God, everything's going on here. What? Let's see. I is a name for a player, as usual. N is the set of players. We've got K1 is to K1 up to K being the dates, not T, because T is going to be for type, I guess. Although we don't use T. T is for type, not dates. Dates are K equals 1 up to K. A for actions, so A sub ik is the set of actions. Capital A sub ik is the set of possible actions for player I at date K. And we are assuming, I guess that's history independent. There's a set of possible informational types for each player I at each date K. There's also a state of nature that exists at any date K. We are going to break in at some point. I'm going to make the states a product set. There could be several. It could be a multidimensional state, and I may want to. I'm going to at some point want to talk explicitly about different dimensions, different coordinates of the state. If so, there are finitely many possible dimensions of the state, and the state space will be a metric space right from the start. At some point, I want you to think that we're trying to think. We want an existence theorem, so having the set of actions be a compact metric space, and the types and the states be a compact metric space are natural assumptions. And please go ahead and make it. But for the basic definitions, I think I only need the metric for the state. And then I can use subscripts by such as when I say A sub less than K, that means the set of all actions for all the players at dates before K. So let's see, a delta of anything is the set of all countably additive probability measures, and is given a set of measurable subsets. If we talk about everything's going to be the Borel sigma algebra generated by open sets whenever we have a topology, and products are given at product sigma algebra as the usual kinds of measure theory assumptions. Nature, we have to say for any history of the states before state K, before date K, and the actions of all players before date K, nature gives us a regular conditional probability function that's a probability distribution over what the date K states will be. So that's what we call nature's probability distribution function, player I's information is given by a type function that maps the histories. I think that I changed that to be strictly less than. The previous, as a function of the previous states and the previous actions, what is his type? And there's a formulation here of what perfect recall is. I don't think I'd want to go. It's not important. Perfect recall is a common assumption. It's hard to formulate. It says that when you know what my type is, you can infer what my type and my action was at any previous date. And finally, there's a utility function that says as a function of the final state theta without any subscript means all the theta states from the beginning of the game to the end, and A without any subscript means the product of all the actions from beginning to end, and we've got a real value utility function that player I wants to maximize the expectation of, given whatever information he has at any point in time. And one can assume that this is continuous is a good assumption, but obviously in auctions it isn't, and so but that's the general definition. Once we've got that, we should talk about strategies. This is an attempt to build up inductively all the induced distributions in sort of the obvious way. Let me just think so a strategy is going to be a regular conditional probability function. These are really behavioral strategies. It says given your type, which includes all the information that you've ever learned, into probability distributions over your own actions. If you're player I at any date k, and it should be a countably additive probability measure on the subsets, and these probabilities should be measurable in the type. And then we talk about product spaces of so I'm trying to use capital S stands for the set of all probability distributions of all such behavioral strategies, and when you take the Cartesian product over all what a player can do at all dates k, then you have player I's strategy space, and just S with no subscript means we're looking at strategy profiles for everybody at every date, and we can have similar notation for all this other stuff. And then we're going to take our probability, the given nature's given probability distributions, and induce a, with any strategy, let's see, for any history up to, before date k, and a history of nature's states before date k, and players' actions before date k, and given the strategy that the people are applying from date k onward, you can talk about what's the probability of any event that could happen on date k. What do the states and actions be? Well, it's nature doing its thing, and the players doing their thing for any product space, and then we extend from product spaces to all measurable states, from product events to all. This is for events that are product events. We can define that the obvious way, and then once you know how to compute probabilities of product events, all the players are behaving independently conditional on their type, and nature is applying her probability, her given probability distribution. And then once I have that, I can now inductively, and this slide here does it inductively starting at the end of the game. I can say, given any history up to date k and any strategy applied thereafter, what's the probability of any sequence of things that happen, in events that can happen through the end of the game, and so finally, P given S, I can build up from these things, multiplying period by period. I can define the probability distribution over outcomes. What are the outcomes? The outcomes are the sequences of states in every period and the sequences of all players' actions in all periods that depend on that's a little s, the strategy, the probability of and I can talk about the marginal distribution on any earlier state, up to any earlier date. At some point, well, to express the dependence on nature's probabilities P, I might write this big P function, which is given a strategy, I might say this is given nature's probability distributions here, and if you change nature's probability distribution, then then you could write that how you're changing it in there. Because one of the problems is for many years we thought one of the things we thought we'd learned after about 3 years was don't ever change nature's behavior. And then this year we learned maybe you do need to change nature's behavior. Yeah.
Super general, so I'm
Sure.
trying to understand.
Right. So this notation, you shouldn't read all those words. Right.
So the games.
Ultimately, we want to get down to this probability distribution, which is induced by a strategy profile. Right.
So the game starts, and we all have private types.
Yeah.
Should I be thinking of games with imperfect monitoring? Can I see what everybody else does, or is that something I also don't know?
You should certainly think of imperfect monitoring. Absolutely.
So I don't know that. So that's another thing I don't know
I
about.
should tell you what I think what we are going to talk about is what we'll call projective games, which are games where essentially you might see some players' actions directly, and if I'm choosing a real number, then there are infinitely many real numbers that you didn't see as soon as you see which one it is. There's infinitely many possible values. but then you might see other random numbers generated by signals that are imperfect, noisy responses of something in the world around us to things that other people have done. And you might get information. My sales performance is an imperfect measure of my effort. I choose an actual.
Possibly evolving as well.
Or
types fixed at the beginning of the game. I mean,
no, types. No. That's John when I try to talk like John Harsanyi did in his Bayesian games paper, I think of the type as being the beginning of the game. No, here I'm using the word type in a somewhat non-standard way to mean it's your information state that evolves over time.
Okay, so what I'm learning about, possibly I'm learning about these fixed objects
Sure.
that started at the beginning of the game, but through a lot of complicated signals.
Yep.
Okay.
But you remember what you did. You have perfect recall. You
Right.
remember
So,
what you did.
and we don't actually use perfect recall anywhere, so evidently it's not that important, or maybe it's not that important, or maybe we haven't done our proofs carefully enough because maybe it is important. Let's see what's important here. I want to talk about observable events. The observable events, first of all, any set of types for any dated player, any player at any date, could be identified with a set of possible outcomes or total histories of all actions and states in the game that would yield such types. There's this function, tau, that depends on the state up to and including, or maybe just up before date k. There it seems to say up to and including. So I can identify any subset of a player's type space at date k with a set of histories that would have yielded it. And in that sense, I can talk about having defined the probabilities of histories given strategies. I can talk about the histories of any measurable set of types that I could have. And those are events that I could observe. But actually, we want to use the word observable just a little bit stronger to say observable events are events which are measurable with respect to a player's type, so that they're things that the player could observe. Some player at some, the states that are observable at player I at date k are the events or subsets of his type space or subsets of outcome space that are measurable with respect to what the player's type, and which for some strategy profile could have positive probability. So I won't use observable to mean things that are in principle observable but could never happen no matter what. And I don't think we have to worry about things what you would believe and what you would do in things that could never happen no matter what, because when I deviate, there's no way I can make one of them happen in my perception. For any event that I can observe with positive probability, there's no way a deviation of mine could make you observe something that would never have positive probability, and me think I have to worry about what you would do there because it has positive probability to me, so it doesn't happen. So those are the observable events, and those are the ones we want to check rationality for. All of them. The problem is there are a lot of them. And for example, you understand that when I choose a real number between 0 and a trillion that could be thought of as a price that I'm going to charge per kilogram of something, that's a compact set, so it feels like it's mathematically a nice set, but it is impossible to have a probability distribution on that set such. I'm going to choose this number, and then you are going to observe it. You hear what number I chose. And it is impossible for me to randomize in such a way that all observable events simultaneously have positive probability, because every single number is observable by you. There is a strategy that would make it have positive probability. The square root of 2 is a number I could have chosen, or the pi, or 3. But I can't. But there's an uncountable infinity of numbers. And it's impossible to have a probability distribution that makes all single numbers have strictly positive probability. That's what gives this its color. So we're going to talk about observable events. Script C stands for the observable events for all players. Y are the measurable subsets of the outcomes. And ultimately, I want to talk about players. So we can talk about players' the conditional probability distribution given an observable event. We've got the machine by dividing through by the probability, take the probability of any outcome event intersected with the observable event divided by the probability prior. This formula says how to compute the conditional probability of any outcome event, conditional on the players using a particular strategy profile and a particular observable event happening. That conditional probability can be defined by Bayes' rule when the observable event has positive probability, and I can talk about if the event has positive probability with this strategy profile, I can talk about the conditional expected value for the conditional expected payoff for the player. So that's a framework, and you weren't supposed to read all that junk, but you were supposed to say, about that long, about that dense should be all the stuff, and if there's something you didn't understand, you'd say, could you please go back, because I'm missing whether something depended on something else or not. We'd go back and look. Okay. Such as, for example, I just realized that I thought all along because I couldn't read on my screen well enough Microsoft Word was putting a little funny underlying thing, like maybe there's something misspelled in every single formula, so I didn't know that strictly, I thought that there were less than or equal to's that meant that my type could depend on the current state. I thought it only depended on past states. But
Underline less
yeah,
than.
so I couldn't see the difference between an underline less than and a less than, because they look the same because of that funny little thing. I'm sorry to bring that up at Microsoft. It's a sore point. I'm sure I could have turned that off. Okay. So now let me give you some the examples should be the most important part. This is a good example. This is Harris, Rainey, and Robson showed that we're going to get what we call strategic entanglement. One thing that's going to be fundamentally different from all of these examples. I think I know what sequential equilibria is supposed to look like, but some obvious ideas don't work, and that's sort of what this is meant to be about. One thing is. So what's going on? There's too much to read, so let me just say. So player 1 and 2 go first. 1 chooses a number between -1 and +1, and 2 chooses left, right. 3 and 4 observe the date 1 choices. I think it's only necessary that they observe what player 1 does. And then they also go left, right. All right. Player, what does this say? Player I's payoff is, let's see, so 1 is choosing +1, or is choosing either a positive or negative number or 0. So players 3 and 4 get, if they get either -a, what player 1 does, or what it 1, either the negative, the opposite of what 1 does, or what 1 does, which means that if 1 chose a negative number, they would like to choose left and get a positive payoff. And if 1 chose a positive number, they'd like to choose right, both of them. Player 2's payoff depends on whether she matches 3's choice. So 3 wants to, I don't know why these numbers are the way, but I think you just say player 2 wants to match player 3. If 2 wants to do L, if 3 does L, 2 wants to do R, if 3 does that. That's all there is. So player 2 wants to match player 3. Player 1 gets 3 things. First of all, this middle term is the biggest one. If 3 and 4 match, he gets 0, but he mismatch, he loses 10. Nothing's going to be bigger than that. Player 1 wants 3 and 4 to match. That's really important. Secondly, second most important, is player 1 wants players 2 and 3 to mismatch. If they mismatch, if he chooses any positive, any non-zero number, its absolute value is between, any absolute value number between -1 and +1. Any number that player 1 can choose, its absolute value is bigger than its square. The square makes it smaller in this range around 0. So this is the third term is less important. He kind of doesn't like choosing non-zero numbers, so that's what the third term, the least important, says. This one says that the middle-sized one is that he would really prefer that 2 should not match 3, because he loses. He gets a positive A1 if the absolute value of A1 if they mismatch. So he really wants to try to make 2 not match 3, but 2 wants to match 3. Okay, so that's the problem. But of course, 2 doesn't see what 1 is doing. So here's what essentially there's no subgame perfect equilibrium in this game. There is an obvious solution. The solution. If you made a discrete approximation to what player 1 can do, he would want to choose the smallest, he would want to randomize 50-50 between the smallest positive number and the smallest negative number. That's essentially what he likes doing. So as to get at least a 50% chance of player 2 mismatching player 1, whatever player 2 is doing with greater probability, he wants to guide player 3 and also player 4 to do the opposite of it. But what's most important is that he wants them to match. So he doesn't want to choose 0 because he wants to. As long as he chooses a non-zero number, if it's positive, they both go left. If it's negative, they both go right. I got that right. If it's positive, they both go right. Excuse me. If it's negative, they both go left. And so he can get them to match. But he doesn't want, and he wants to randomize because he doesn't want player 2 to know, but he also wants it to be the smallest possible number. So then what happens? You could take discrete approximations, but in the limit, what's going to happen is player 1's always choosing 0. Players 2 and 3 are randomizing 50-50 between, players 3 and 4 are randomizing 50-50. I'm sorry, players 2, 3, and 4 are all randomizing 50-50 between left and right. However, 3 and 4 are both independent of what 2 is doing and necessarily independent of what 1 is doing when he's always choosing 0, and yet they're perfectly correlated. So what's correlating them? The answer is the infinitesimals. So we get what we call strategic entanglement, that players 2 and 3, it looks like players 2 and 3 are not behaving independently, as if they're getting a correlating signal that you can't see in the limit of the equilibria. So what we learn from this is that maybe we're not going to talk about sequential equilibria, we're going to talk about limits of epsilon approximations to sequential equilibria, and because it's important to define strategic independence, that I cannot use information that I don't have. But in the limit, we might find that it looks like I am, like players 3 and 4 in that game, I am getting information that I don't have. Let's see, what's this? Example 2. I should do the limits of step strategy approximations. Going through all these just an hour ago, and I've already forgot. It's a zero-sum game. Player 1 chooses a number between 0 and 1. Player 2 observes player 1's choice and chooses a number between 0 and 1. And player 1 wins if their choices do not match, and -1 if they don't. Oh, I see. Yeah, the player 2 wants to match what player 1 did. It's a discontinuous game, but here's a line. It could be a reduced form of a continuous game with another stage. If you just say, I observe both of you guys, and then I decide what your payoffs are in some bounded interval, I don't care about anything, then I could do this. I could say, if they match, then player 2 gets 1, and 1 loses, loses. And otherwise, if they mismatch, then player 1 gets the reward. So it seems obvious, since 2 observes 1's action, she should be able to win. One's in trouble, he's going to lose. But if you made any fixed partition of 2's type space, then player 1 could randomize over a large enough finite set of actions so that within each partition, so if you tried to make a discrete approximation of what 2 could see, if you gave player 1 the opportunity to mix within what she can see, that would be a problem. She would like to use the strategy A2 equals T2. This strategy can't be approximated by any discrete game where she has finitely many actions and finitely many partitions. So you have to kind of allow, either we look at the whole game or we look at we allow strategies like this. And so we're going to have to bring in all if we don't, let me just remind you, this is an introduction to an attempt to define a solution concept that doesn't exist in game theory. You could say, just look at the limit of some sequence of things. Well, one answer is pick a sequence of a way to define a sequence of approximating games. And one obvious thing is wherever a player has information, take sequences of nets of finite partitions and nets of finite subsets of their actions, restrict them to like get a finite game that applies to a la Kreps and Wilson, apply Kreps and Wilson there, and take all the weak star limits or point-wise, net-wise limits of those things, and that's it. And I can't argue that's wrong. In fact, I've often argued that's right, because I've been the guy who wanted the existence theorem more than my co-author, I admit. My co-author, I think, is better to the laudable principle that we should actually have some intuition, we think. And maybe you disagree about the intuition. But I think the intuition was, damn it, player 2 observes player 1's action and she wants to match, and he doesn't, he wins, she wins, he loses. That's it. I should say, by the way, I don't know if you. I always think even numbers are nice female names, and odd numbers are male names. That, you know, that in case so player 1, player 2 is obviously a she. I mean, obviously, sometimes boys have girls-sounding names, and girls have boys-sounding names. But 2 is a girl's name. Anyway, so obviously she wins in this game. If that's your intuition, then you can't. Then we must begin to essentially allow strategies like this to come in, and we're not going to be able to do it by finite approximations in a whole bunch of obvious ways. Well, this was spurious signaling. Oh, this is interesting. Here's there's a state. Players 1 and 2. The game players are 1 and 2. Nobody observes the state. Wait, let me think. Player 1 observes nothing, and he chooses an action that's a real number between 0 and 1, and player 2 observes either the number that he chose or the square of that number, depending on whether the state is 1 or 2. Player 1 would like to persuade, then player 2 she looks at what she learned, which shouldn't tell her anything, and she wants to choose 1 if it's state 1 or 2 if it's state 2, but player 1 would like her to always choose 1. So, and 1 is the less likely state. It has probably 1/3, whereas there's a 2/3 probability of state 2. So he can't persuade her. He's got no way to, any number he could send her, he could send by doing, you know. But if you make finite approximations, then there's always some number there's some highest feasible number he could choose that's just a little bit less than 1, whose square would be less than it, and that would be taken as a signal by player 2 that this is state 1. So we call that spurious signaling, that somehow he's able to persuade her of something if you look at finite approximations. These examples indicate that attempting to approximate a true game by a finite game is unreliable because it can produce unwanted equilibria. In a variety of ways, there are many words here about taking finite. If you have any finite partition of player 2's information structure and any finite set of actions that you allow player 1 to choose, there's a way of refining the information structure and adding one more action to player 1 such that player 1 would want to now choose that action, and he would signal it to at least when it's state 1 to persuade her it's state 1. But then in the real game, if she were persuaded, then of course he would like to choose a number that's the square root of that number, which is just a little bit higher, a little bit closer to 1, and because he'd rather persuade her it's state 2 he'd rather persuade her that it's state 1 when it's really state 2, because he knows state 2 is more likely, so he'd like to convince her of this falsehood. She'd like to convince her of this when it's false rather than when it's true, because all he cares is he'd like to convince her. He doesn't care in which state, so he'd like to do it in the more likely state. So it doesn't work. And finite approximations just lead to ridiculous outcomes. This is the example that bothers me the most. And I will show you. So let's see. Maybe I'll skip forward from it for a moment and come back to it. Yeah, I think I'll. The need to perturb this example. This is a good example 5 for a moment. This example takes me. We convinced ourselves that it was dangerous to perturb the workings of nature, and then we came up with this example. Consider the two players are going to play the Battle of Sexes game, and player 1 prefers what is it? The RR. I was the top bottom. This is left right. What does it say? Player 1. Oh God, the double subscripts are confusing me. I see. Player 1 at the first stage. It looks like the Battle of Sexes game, but player 1 goes first. You might think player 1's going to win, but no. Player 1 chooses left-right. If he chooses left, that's up here. That's the one he doesn't like. Then nature chooses a uniform 0-1 random variable. But if he chooses right, then player 1 gets to do a second thing. He gets to choose a number between 0 and 1. In either case, player 2 moves next, and she observes either nature's number if 1 chose left, or she observed, which is between 0 and 1 uniformly, or she observes player 1's choice if he chose right. But she doesn't observe his choice. There should be an equilibrium in which she says, I'm player 2, I think we're going to the equilibrium that I like better. I think he's going left. Therefore, when he goes left, he doesn't get to choose a number. Well, the number I'm seeing is chosen by nature, uniform 0, 1 random variable. That's it. That's what I think. I believe that. Therefore, I'm going to go left. And player 1 should say, no matter what, she's going to think the number was chosen by nature. And I lose. Therefore, I better go left. So that seems like a reasonable sequential equilibrium. There's another one where he goes right, and she sees a number. You can do whatever number you like that he then chooses, and she's convinced. Either way. But we're going to have to perturb how do we do Bayes' rule to check whether these inferences are valid? Well, if you leave nature alone, any number that she observes is an observable event because he could choose it. He could go left and choose that number. But that's the only way it has positive probability. So if we're going to perturb slightly the strategy to get things to have positive probability, to check if the way we generate beliefs is by perturbing behavior a little bit, just as Kreps Wilson did, then we discover every single number has to be taken by player 2 as an inference that player 1 chose right. And therefore, she should go right, which is what he prefers, and suddenly the equilibrium is gone, because now any number will work. Now, it's true that just the event that she's observed a number between 0.4 and 0.5, for example, has positive probability. And there she would be perfectly allowed to infer that it was nature. But for every single number, if the only way we know how to perturb the game is by perturbing people's strategies to get things to have positive probability. Kreps and Wilson taught us we're going to figure out what beliefs are by having people make small probabilities of mistakes. And if it's only people making small probabilities of mistakes that are used to generate positive probabilities to compute what people believe, then player 2 always has to believe that it's right for every single number. And since we have to account for what she would do after every single number, that's what a strategy does, then we come to the conclusion that she always goes right in response to believing that he went right. So that's ridiculous. What we're going to have to do is allow perturbations by nature. Yeah.
You can't help things here by forcing him to perturb over a set, or I mean, it's the single number thing that's a problem, right?
Well, you're right. That's where. This is as good a place as I know. I don't have to cover every single example that's problematic. One of the things that's going on. That's good. So one thing I would suggest is perhaps we could talk about she only has to make inferences like over open sets. And in the discrete case, with discrete topology, every single point is an open set. That's a good. I'm glad I switched the order, because the next example, the previous example that I skipped over, is one that among other things gives us something on that. But right. So let me just pause and make sure everybody gets what you were saying on this guy. That nature can make for instance, any open interval have positive probability after left. So if we just make sure that her strategy would make sense when you don't tell her what the specific number is, but for any open interval, and when any open interval includes arbitrary small open intervals around that. There are a couple of problems with that. I think the next one has a problem with that also, which was, so this is Harris, Stinchcomb, and Zame's example in 2000. Player 1, there's a nature, there's a kappa and a theta that are the state of nature in the first period. Kappa is either plus or minus 1, call it the important state, and theta is a uniform 0, 1 random variable, uniform and independent. Player 1 observes the theta, and he chooses an A1. He doesn't observe the state. Player 2 then observes what's the absolute value of how far is A1 from theta times the state? So as long as player 1 misses theta, player 2 can, by positive or negative, know the state. She chooses -1, 0, or +1. And she wants to minimize the squared error from the kappa state. And player 1 wants her to choose as close to 0 as possible, please. So player 1 wants her to be ignorant and therefore choose 0. But if he misses the theta, then she gets it. So if we only talked about open sets, then consider a strategy profile. Can there be a sequential equilibrium where he misses? One answer is he just hits 0, and she, and that seems to like the obvious solution. He chooses the strategy match theta, A1 equals theta. She gets 0. She chooses 0. He's happy. That's it. But consider the following strategy profile. He chooses 1 all the time. Player 2 then goes 1 if she sees positive, and -1 if she sees negative. But if she sees 0, she also goes to 1. So now player 1 says, I guess it doesn't matter. I might as well choose 1. No matter what happens, no matter what she sees, she's going to choose 1. We can tremble things to make this sequentially rational everywhere except at 0. And at 0, she's doing 0 when she's doing +1 when she doesn't know when she should do 0. You say, well, here's how it could be sequentially rational. Consider a perturbed game where there's just a tiny probability that kappa and theta both equal 1. With some little probability, just put a little bit of tremble into nature. Then learning if she sees 0, what does it say A1 equals theta? Learning that A1 equals theta learning that she sees a 0 means she knows A1 equals theta. That causes 2 to believe that kappa is 1 because she thinks player 1 is choosing 1, and therefore she chooses 1. That's sequentially rational. The way to get around this, so one thing I want to say is, first of all, it's really important to ask what does she infer on 0 itself and not just on open intervals around 0, because also we could get her doing anything if we didn't ever talk about 0 by itself and had it 0 exactly be a 0 probability event within the broader interval. But the other possibility is, what we argue for this is, just as we're not going to let players, when they tremble, to convey information about things they don't know, we may want to let the state of nature be divided up into components where a tremble in one doesn't tell you anything about another. That the change in the theta doesn't tell you anything about the kappa. And so we come up with a class of models where we are going to allow perturbations of nature. Let's see. I guess we're supposed to end at 1 o'clock, so maybe I should give the definition rather than any more examples and say this is the best we got. We define an epsilon close perturbation of nature to be something where, what the key is right here, we're going to perturb nature's components independently. As a function of where the component is, we could move it a little bit, but with probability at least 1 minus epsilon, you leave the state the same. This should say KH given K. This is KH. Those subscripts should match. You stay where you were. K. I don't know why this is all messed up. This should say that the perturbation leaves the theta the same, and this should say that with probability 1, the distance that you're perturbing the state is not more than is less than epsilon. So apologize, I'll correct that. And then our definition of an epsilon sequential equilibrium that's hard to prove existence of because it involves a kind of uniformity is for any a strategy profile is an epsilon sequential equilibrium if, so this is the best we can do today for matching all the 7 examples of which I had a chance to discuss 5. If for every finite subset of the type spaces, for every finite collection of observable type space events, so these are events that at least one player could observe and which could have positive probability under some strategy. So we want to say for any one of them, for any finite collection of them, there exists an epsilon perturbation of the S. That is to say, we're going to take the strategy profile that's fixed And we're going to say, oh, with 1 minus epsilon probability, they do that. But with epsilon probability, maybe they do something else. And the something else might depend on the finitely many things that we're going to worry about. And we're going to make all those finitely many things have positive probability. Also, with probability epsilon, we can perturb, at any history of the game, we can perturb nature from what she was going to do and say, with probability epsilon, maybe she doesn't do it, but she does something that's within an epsilon ball of what she will. So we're going to let nature provisionally choose her outcome, and then we're going to step in and say, oh, well, maybe with probability epsilon, we change it a little bit. So the perturbation of the strategy and the perturbation of nature is allowed to depend on which finite collection of events you choose. And you choose any finite collection of events, I've got to be able to find any finite collection of observable events, I've got to be able to perturb my sequence strategy profile a little bit and nature just a little bit in this way, so as to make all of your events have positive probability, so we can do Bayes' rule. And then for any strategy that is a date k continuation of future continuation of this observable, in date k by player I and date k, player I's strategy is within epsilon of the best he can do. Anything else he could do by continuing in the future to behave differently cannot be more than epsilon better than what he's actually getting. So epsilon appears a couple of times in this story. And that's the definition. Let me just say, it's sad that I won't say it. You can then talk about pointwise and pointwise limits of these distributions, which then become finitely additive measures. In the example one, the example where they became strategically entangled, we got a finitely additive measure, not because for every delta between zero, strictly positive, there was a probability one that player one was strictly between 0 and delta, or probably half that he was strictly between 0 and delta in that story. And yet, when delta goes to 0, the accountable intersection of these is the empty set. So you have probability halves vanishing because there's no probability at 0. Or you can take the weak star limit, and then you just get the strategic entanglement properly. And let me just say we have a very weak, that's a weaker concept. I'm going to skip that. Here's a class of games that essentially says that everything, let me just say, this is the class of games called regular games with projected types, and the regular has the property that basically all the 0 probability events anybody's generating are from specifically observing people's actions and saying, oh, I thought there was a 0 probability of you doing that. That's a surprise. And all the other stuff that people observe is coordinates of nature, where the positive probability events are the same as if, for example, I don't know, I can't talk about normal distribution because these are compact sets, but talk about a beta distribution that has full support all over, no matter what it is. You have a beta distribution. You can have an arbitrarily high probability in a beta distribution near any one point in the unit interval, but not anyway. But everything. So in some sense, the 0 probability events are independent. That nature generates are independent of the strategy, and the only surprises in this class of models are those that are coming from observing actions directly, and for that we have some existence theorems. So the allotted time is over. I'm going to switch back to example 4 that I thought was interesting, if anybody was willing, but I'll say it's socially acceptable to leave and to sign off, or I can talk for 3 more minutes or two like that. Okay.
Oh, yeah.
So this is an example that really bugs me a lot. There are two teams and a referee. Let's see, players. The even team consists of the odd team is players 1 and 3, obviously boys, and 2 and 4, the 2 girls, the girls team, and players 1 and 2 each choose an action between 0 and 1 in the unit interval from 0 to 1 at date 1. 3 and 4 choose an action at date 2, and each player observes the first what is his. Each player observes what his or her teammate did, and so 3 observes what 1 did, 4 observes what 2 did. The referee is player 5, who is equally likely to observe the choices of team 1 or team 2, but he doesn't know which team he's observing. He observes, either the 1 and 3 choices or the 2 and 4 choices, and then he chooses a number that's either 0 or 1, which is the payoff of the people who he's observed. So he just decides. So imagine a game, for example, where player 1 says, "I'll pay you if you," I don't know. Let's see. What does it say? It should not be. So there's some set of x, y numbers that 5 could observe where he's going to say 1, and then players 1 and 3 want their number to be in that set, and players 2 and 4 want their number to be in that set. It should not be possible for the odd team to receive a payoff close to a half, which means getting money all whenever they do, without the other team being able to do so. Let's see. However, for any finite partition of the player's type spaces, and since 3 is observing 1 and 4 is observing 2, they're logically observing different things, and you could partition it differently. Let's see how to get to a very specific example. For example, let's just all read. Let x and y be distinct actions for some common element of 4 is partition. Yeah. So there's something that player 4 cannot distinguish in a finite partition. Consider strategies that give positive probability to all partition elements and also satisfy the following. Players 1 and 3 put most of their probability on player 1 doing x and 2 doing it, and 3 then responding with x, and they win. Player 2 is putting most of her probability to, when she's in this set that has x and y, she's putting most of her probability to y, and player 4 is responding with y, and 5 says, I'm only going to pay off when I see xx. Well, player 4, when she sees this event, she thinks, x and y are both possible numbers. She thinks it's probably y, and we're going to lose. So why should I might as well do y. If you like, you could have player 5 have a small probability of rewarding y, but so I think it's probably y, so I better match her. Better match. Well, the problem is we can't talk about every single event. So what happened? In the definition, this is what drove us to something a little funny. The definition, so with this in mind, if you have a strategy where 1 and 3 are winning with high probability, the event, there's an action that player 3 could do matching 1 that causes a victory for, well, if she could just, if player 4 could also see her teammate doing the same thing, she would also want to match and win. Where's the definition? So that's why the definite, oh no, keep going, go to the definition, there it is. That's why the definition says, first you have the behavior of the players, and then we have to talk about, with only small perturbations, it has to be sequential rational in all events. Once we've got this, if there's an event where players 1 and 3 are likely to win, then player 3 is part of what she has to see to make that go. Once I allow the possibility that the player 4 seeing that is also in the finite set, then 4 has to be winning. It has to be grabbing and winning, and then her teammate 2 has to be saying, yeah, let's go in that event because then we'll win. So then 2 and 4 have to be winning also. So it's a little subtle, but we have to. That's why the quantification, and this is the harder to prove existence of it. It bothers me a lot because I like easy things that are easy to prove existence of. That because of that example, it seems like first once you tell me the strategy space, the strategy profile, that tells me something about what are some important events I want to make sure certain players observe. If players 1 and 3 are winning with a certain kind of strategy, then I want 4 to be able to observe 2 and 4 to be able to have the same information that 1 and 3 have respectively, in they're implementing that strategy. Also, the other thing I would say is that makes this hard to prove existence is we're talking about that there's no finite approximation in this epsilon optimality. The epsilon is an obvious relaxation, and we feel you need that because you have to allow people to make mistakes in order to have the possibility of making things that are dumb have positive probability in order to verify that they really are dumb things to do, because if you made them happen, people would rationally behave badly. So we have to allow for some small probability mistakes, but this is over all possible. There's no restriction on the strategies that a player can deviate to, and if there was any complicated strategy that a player had, which in one of these test events in script F, then that would make it better, that would make it much better, substantially better, by more than epsilon, then we fail the test. So that in this sense, we're not looking at, for both the uniform, the F's are quantified after the S is chosen, and because we're considering all possible strategies, it's not really a limit of approximations of finite of any sequence or net of finite games that we can understand, and therefore existence proofs are much harder. and are, as I say, only for a rather weak, a broad but not broad enough class of games. Let me just say to finish that I think we'd like to come up with a definition which can prove existence, at least for a class of games that includes most of the examples that are in the applied theory literature, because that's the hole we're trying to fill. And we'll be pleased if we can. I thank you for letting me talk about this. There may be something we are missing. Let me go back to the very beginning and say at the end, these notes are all on the Meyerson Research Chicago website, the address that's on this page that you can see. And if anybody downloads this and looks at it and says, they're off, there's another way of looking at this that would make everything clear and we could prove existence much more easily, please let me know. You might be right. Just because I've been thinking about this for decades and other smart people have been thinking about it for decades doesn't mean there's many simple ways of looking at things, and we have not considered all simple ways of looking at things. And we may have been bringing some prejudice to it that you mercifully are free of, and let me know. So, thank you.